Bismillahirrahmanirrahim. Assalamualaikum and selamat sejahtera everyone. Now let's start our revision for Zero to Hero Ionic Equilibria. Question number 1. Identify the conjugate acid-base pair for the reaction. As we know, the N2H4 is the weak base. Okay, because how do we know it is weak base? Something that consists of nitrogen and hydrogen, they are ammonia derivatives. So basically, ammonia derivative will form a weak base. And when they dissolve in water, it will partially dissociate because it is weak base. Okay, so this water produce H plus and OH minus. The H plus will go to the N2H4 and N2H4 receive the proton. While N2H4 receive the proton, it is the characteristic of base. So after receiving the proton, it will form N2H5 and OH minus from the water. So the partner will be conjugate base, a conjugate acid, and the OH minus produced. So basically, the conjugate is something that produced from the dissociation of acid and base that located in the product part. Okay, while acid and base is located at the left side at the reactant part. So now, conjugate pair between the base is N2H4 is the base, conjugate acid is N2H5 after receiving the proton, while the acid is water, and after losing the hydrogen, it will form OH minus, which is the conjugate base. For question number 2, you are given 0.018 aqueous solution of ammonia is the weak base, and the concentration of hydroxide ion is 5.6 molar hydroxide ion. Write the equation for the dissociation ammonia in water. So this is the ammonia as a weak base dissolved in water. Reversible arrow because it is partially dissociate. Then the ammonia is a base. Base according to Bronsted-Lowry acid will receive proton. So after ammonia receiving proton, it will be NH4 plus and then produce OH minus. Okay, don't forget the phase. For ammonia, it is aqueous, water is liquid, NH plus aqueous, OH minus aqueous. Therefore, here 1 mark for your equation, correct equation with the phase. Okay, this pair is 1 mark, another pair of acid and conjugate base is 1 mark. Okay, question number 2, determine the pH of the ammonia solution. First, we need to write down the ammonia dissociation equation. Just now we have write, and then the pH, because this ammonia is a base, so base ammonia we cannot calculate the pH. pH is negative log concentration hydroxonium ion. But because ammonia is base, does not produce hydroxonium ion, it produce OH minus, then we can calculate the pOH. So what we need to do is to calculate the pOH first. pOH is negative log concentration OH minus, and the concentration of OH minus is given negative log 5.6 exponent negative 4. Therefore, it will be 3.25. Remember, this is the value of pOH, but the question need you to find the pH. Therefore, pH will be 14 minus the value of the pOH, 3.25. So it's equal to 10.75. Here you will get how many marks? 1 mark for the formula or your substitution. 1 mark here, 1 mark for the pH, 1 mark for the formula 14 pH plus pOH equal to 14 or pH equal to 14 minus POH. And the fourth mark is your final answer. To C is calculate the KB for ammonia dissociation. But based on your dissociation equation, we substitute into the KB expression, and something that we need to substitute, the value that we need to substitute into the KB expression must be the concentration at equilibrium. Therefore, we need to construct the ice table of concentration. Okay, I repeat, whatever value substitute into the KB expression must be refer to the concentration at the equilibrium. Therefore, we need to construct the ice table. Okay. So, do we have the initial concentration of ammonia? It's given from our equation, from the soalan, 0.018. At first, liquid does not involve, so we just put dash because it is pure liquid, concentration does not change. And then the concentration of ammonia is 0 because ammonia and hydroxide ion haven't dissociated. And then it will dissociate by value of x. Okay, changing by x, so it will be minus x. And then increase by x for the hydroxide ion. And at equilibrium, it will be 0.018 minus x. This one is x. Okay, how to find the value of x when you want to substitute into the KB expression? Given the concentration of the OH minus is 5 exponent negative 4 molar. That is refer to the concentration of the hydroxide ion here. So we know the value of x is 5.6 exponent negative 4. Therefore, we can find the concentration ammonium ion and hydroxide ion at equilibrium. 0.01 minus 5.6 exponent negative 4. This one 5.6 exponent negative 4. Finally, the concentration of ammonia at equilibrium will be 0.017 molar. Now, let's substitute into our KB expression. The concentration of hydroxide ion 5.6 exponent negative 4, and the concentration of ammonium ion also like this. Just divide by ammonia concentration at equilibrium, 0.0174. Like this. So our KB will be, tekan calculator, you akan dapat 1.8 exponent negative 5. So that is the value of KB. No need to put the unit. Okay, what about the marks? We are going to get 1 mark when you find the concentration of ammonia at equilibrium, 1 mark concentration of the ammonium ion and hydroxide ion at equilibrium. The other marks is substitution or the expression, 1 mark. And then final answer of your KB, 1 mark. Next, we proceed with determine the percentage of ammonia, percentage ionization. So as we know, the formula of percentage ionization is the concentration of ammonia that dissociate or ionize over the initial concentration of ammonia, initial concentration. Now, the changes of the dissociation is referring to the value of the changes here, x. So the x is 5.6 exponent negative 4. Right, 5.6 exponent negative 4 over the initial concentration 0.018 molar. So here is molar cancel times 100%. Finally, you get 3.11%. Question number 3, we need to calculate the pH of the buffer. This buffer is acidic buffer that made up of 10 gram sodium cyanide as a salt in weak acid HCN. So now let's check whether it's is a buffer or not a buffer. Normally we take the acid HCN. So dissociation of weak acid need water, reversible arrow. HCN will form Cn minus, and then the H plus of this one will combine to the H2O to form H3O plus. While the salt NaCN is completely dissociate to form Na plus and an ion Cn minus. Now this is the weak acid as a first component, and the second component is the conjugate base. The conjugate base having the same ion from the salt, having the same ion with the conjugate base of that come from the weak acid. So we can conclude that it is a buffer, acidic buffer. Now to calculate the acidic buffer, we need to use the Henderson-Hasselbalch equation. pH is equal to pKa plus log weak acid. Concentration of weak acid is concentration HCN as a weak acid, and the concentration of the conjugate base. Conjugate base is the Cn minus. Now, when we know we need to find the pH for this buffer solution, do we have the concentration of Cn minus? We don't have. And do we have the concentration of the HCN? Of course we have, because it's given from the question. So now the missing item here is the concentration of the Cn minus. Now let's find the concentration of this NaCN. Given the mass of the NaCN is 10 gram. So we can find the mole of NaCN is 10 gram divided by the molar mass of the NaCN, which is 49.0 gram per mole. Therefore, the mole NaCN is 0.204 mole. Next, we need to find the molarity of NaCN. 1 mole NaCN will produce 1 mole Cn minus as a conjugate base pair. So here, referring to this one, 1 mole NaCN producing 1 mole Cn minus. If we have 0.204 mole salt NaCN, then we are going to produce 0.204 mole of Cn minus. So molarity of Cn minus is 0.204 mole dissolved in the aqueous solution, which is 500 ml. It is 0.5 liter. So the concentration of cyanide ion is 0.408 molar. Then we can substitute here. Okay, now substitute. Because this is pH for acidic buffer, we need to use Henderson-Hasselbalch equation. We cannot use the negative log concentration hydroxonium ion. Okay, pKa is negative log Ka, 7.1 exponent negative 4 plus log the salt that calculate here is 0.408 over the concentration of the salt, the weak acid given 0.5 molar. So finally the pH is 3.06. Okay, how to get the marks? You will get mark when you find the number of mole of the sodium cyanide, then 1 mole for the concentration of the cyanide ion, Henderson-Hasselbalch equation or correct substitution, 1 mark, and finally pH of the... Let's proceed with question number 4. For question number 4, 0.214 gram of monoprotic acid dissolved in 25 ml of water and titrated with the 0.1 molar sodium hydroxide. The sodium hydroxide required to neutralize the acid solution is 27.4. ml. Then question us to find the molarity of the acid. What is the molarity of this acid? The number of mole of acid is equivalent to the number of mole of the base required to neutralize for this acid. So we need to find the number of mole of the base required to neutralize the acid first. Okay, so that we can get the number of mole, then the number of mole of the base required can be determined with can determine the acid mole. So mole of sodium hydroxide is equal to N equal to mv, and molarity of sodium hydroxide 0.1 molar times volume 27 is 0.0274 liter. The number of mole sodium hydroxide is 2.74 exponent -3 mole sodium hydroxide. Okay, since that is a reaction between the acid Ha and sodium hydroxide, it will produce 1 mole of salt, Na, this one, Na, combined with an ion of acid plus OH, and this H become H2O. We can see here the number of mole, 1 mole acid will react with 1 mole base. From the equation, 1 mole acid Ha can be neutralized by 1 mole of sodium hydroxide. The sodium hydroxide required is 2.7 exponent -3 mole sodium hydroxide. That means we need the same number of mole of acid. So the number of mole of acid is 2.74 mole. Inside here is 2.74 mole. Sorry, again. 2.74 exponent -3 mole of acid. Since we know the number of mole of acid and the volume is 25, we can find the molarity of the acid. Number of mole 2.74 exponent -3 mole over the volume is 0.025. 25 ml convert to liter, then we will get the concentration will be 0.11 molar of weak acid. Here we go to the marks given. 1 mark if you write down the chemical equation. Where's your chemical equation? This one, 1 mark. Number 2 is the second mark will be when you find the number of mole of the base, the sodium hydroxide used, and then the number of mole of the acid being neutralized. Kat sini kena ada mole of the acid, 1 mark, and finally the concentration of the acid, the 4th mark. Here we go to the question 4b. We need to calculate the pH of the solution if 40 ml of sodium hydroxide is added. After 40 ml sodium hydroxide added, 0.1 molar sodium hydroxide added, do we know which component is left at the end that contribute to the pH? It's either acid or the base. So we need to know which component, acid or base, left at the end of the titration. Now let's see, this 40 ml added to the acid is how many mole? Therefore, we need to calculate the number of mole of sodium hydroxide. Before that, we need to construct the ICF table in terms of the number of mole, because we need to determine the final mole of the acid and base. as I said, as I mentioned before, the last component will determine the pH. It's either acid or base. Okay, now calculate the number of mole of sodium hydroxide. The number of mole N equal to MV. Molarity is 0.1 molar times volume of the base given. 40 ml, 0.04 ml. So it will be 0.004 mole of sodium hydroxide. Initially, the salt haven't formed, so it is 0, water also 0. From the balance equation, 1 mole of acid will react with 1 mole base. Therefore, here we have this number of mole of acid and base. If you can see here, the number of mole of acid is less than the number of mole of base. That means the acid is completely consumed or finished during the neutralization. Therefore, we minus 2.74 exponent negative 3, and sodium hydroxide use also 2.74. This is the number of mole sodium hydroxide used to neutralize the acid, and it will form the same number of mole of salt, plus 2.74 exponent negative 3. So yang ni tak payahlah, water ni tak payah. Okay, now we can determine the final number of mole of acid and base. Finally, the acid is finished, it is 0, and the number of mole sodium hydroxide left after the neutralization is 1.26 exponent negative 3. So we just take the initial minus the change, and we get the number of mole of base left. And the salt produced is 2.74 exponent negative 3. Therefore, there is no acid left at the end of the nitration, and the remaining is base. So the excess base will determine the pH of the solution. Since base is left, we cannot calculate the pH, but we calculate the pOH. pOH is negative log concentration OH minus. Our sodium hydroxide dissociation is strong base. It dissociates completely to form Na plus and OH minus. Then the number of mole sodium hydroxide is 2.74 exponent negative 3 mole, and the number of mole hydroxide also will be the same number of mole, meaning that 1 mole of sodium hydroxide produce 1 mole of hydroxide ion. We have 2.74 mole of this one. We also produce 2.74 mole exponent negative 3 mole of sodium hydroxide. But to calculate the pOH, we need to find the concentration of the hydroxide ion. Concentration hydroxide ion is the number of mole 0.019. Salah pula. Tadi yang kita kira tadi 2. The mole as base left is 1.2. This one 1.26 exponent negative 3 mole inside the solution. After we add 40 ml, now the total solution is 65 ml. So this number of mole of the base is located in this 65 ml solution. Okay, because this is concentration mole over liter, it is 0.065 liter. That means the concentration of hydroxide ion is 0.01923 molar. Masukkan dalam pOH. pOH is negative log concentration. Negative log 0.01923 molar. The pOH will be 1.72. Okay, 1.72. Tapi soalan bukan tanya pH, we need to find the soalan tanya pH bukan pOH. So pH is 14 minus 1.72. That means the pH will be 12.28. Okay, where is the mark yang kita akan dapat? First mark is when you find the number of mole of the sodium hydroxide added. And then the final mole of sodium hydroxide. Here, student need to realize that the OH minus is remain at the end of the neutralization. And then another mark will be the concentration of the hydroxide ion, POH, and the pH. So 5 marks here. Explain qualitatively the pH of the solution at equivalent point. Now we need to know at equivalent point what do we have? It is the reaction of the acid and base. The weak acid is Ha plus the base is sodium hydroxide. So this reaction will produce salt, this one, Na plus OH minus H plus A minus. So this Na plus will combine with the A minus to form the salt and water. So when reach equivalence point, the solution contains salt solution. So how to determine the salt solution? How to prove that it is salt solution? Okay, kita tuliskan dia punya chemical equation. So mana salt dia? Inilah salt dia. This one. So this salt is Na plus and A minus. Because the salt, since the salt from the weak acid and strong base, the A minus, the anion A minus will undergoing the hydrolysis, forming OH minus. So how to prove that the anion will undergo hydrolysis? Now let's check. This Na plus is come from the NaOH, while A minus is come from the weak acid Ha. So since it is weak acid, therefore A minus is strong conjugate base, while NaOH strong base producing weak conjugate acid. So we take the strong conjugate because only strong conjugate will break the water. So takes this A minus strong conjugate base, A minus will react with water, break the water to form Ha, this one H plus OH minus. This H plus will combine with this one, producing OH minus juga. At the end of the reaction, we are producing the OH minus. Thus, the salt is the basic salt with pH more than 7. Let's move to question number 5. To help you visualize what is happening in this question, we can refer to this figure. Okay. Calculate the molar solubility of calcium fluoride in 25 degrees Celsius in 0.01 molar calcium nitrate. Okay, now let's solve the first part of this one. Later we compare. Alright, question asks you to find the molar solubility of this calcium fluoride if we dissolve this calcium fluoride inside the solution. This solution is 0.01 molar calcium nitrate. We can see that in the solution, it consists of calcium 2 plus ion and nitrate ion. We can identify the common ion. Common ion means the ion in the solution similar to the ion of the salt that we want to dissolve. Here, the common ion is calcium 2 plus from the salt and the calcium 2 plus inside the solution. So, now let's calculate the molar solubility of the calcium fluoride inside this solution. Let's assume that the molar solubility of the calcium fluoride in this solution is X. So we write down the equation of dissociation calcium fluoride, and our equation must be reversible because not all of the calcium fluoride can dissociate to form their ion. Well, this dissociation will produce 1 mole of calcium 2 plus ion and 2 mole of fluoride ion. So it will form X mole of calcium 2 plus and 2X mole of 2X molar of fluoride ion. But there is 0.01 molar of calcium 2 plus that is already inside the solution that we want to dissolve, which is 0.01 molar. So this is coming from the solution and this X is coming from the salt. So it will be concentration of calcium 2 plus will be 0.01 molar plus X. Again, this one come from here, this one come from the salt that we want to dissolve. Right, now let's substitute this value to find the molar solubility, which is the value of X. So let's find the value of X by substituting into the KSP expression. Okay, the concentration of the calcium is 0.01 plus X times 2X and power of 2. Because stoichiometry coefficient is 2, it's equal to the molar solubility and is given 3.9 exponent negative 11. Please be noted that this is exponent negative 11, which it shows the dissociation of the salt is very, very small. So we can use approximation instead of using quadratic. So let's use approximation. Assume that 0.01 plus X close to the initial concentration 0.01. So now let's solve the value of X. It's equal to 0.01 times 4x squared. So x, square root x will be 3.1 to exponent negative 5. So the x is referring to the molar solubility of calcium fluoride. So molar solubility must be in the unit of molar. Okay. So we have done our first part, which calculate the molar solubility of this calcium fluoride inside the calcium nitrate. Now, let's move to the second part, which we need to find the calcium fluoride solubility in pure water. In this case, calcium fluoride is dissolved in pure water. In pure water, we only have H plus ion and OH minus ion. We can identify there is no common ion that is similar to the salt that we want to dissolve. So, now let's calculate the molar solubility of this calcium fluoride. Let's assume the molar solubility of calcium fluoride in water is Y. Therefore, we can find the concentration of calcium 2 plus is Y, while fluoride ion is 2Y. Now, we substitute into our KSP expression. We will get this, and then this one equal to this one. Solve the value of x, we will get 2.14 exponent negative 4 molar. That means the molar solubility of calcium fluoride inside the pure water is 2.14 exponent negative 4. So back to the question. Question asks to compare the difference of solubility calcium fluoride in calcium nitrate and the solubility of calcium nitrate in pure water. So this is the value of the X in calcium nitrate and molar solubility in calcium in water. So we can compare them. We can see the molar solubility of calcium fluoride in calcium nitrate is lower than solubility of calcium fluoride in pure water. Look at the value. This is exponent -5. This one is exponent -4. That means it is higher solubility, higher molar solubility of calcium fluoride in pure water. Okay, why is it calcium fluoride low molar solubility in calcium nitrate? This is due to the presence of common ion calcium 2+, which is similar with the ion present in the calcium fluoride. So, kalau ada common ion merendahkan solubility. So, disebabkan kita ada banyak calcium 2+, satu daripada garam, satu lagi calcium 2+ daripada solution, banyak concentration calcium 2+ will cause the system to shift to the left. If shifting to the left, it will form more calcium fluoride. It is solid, so we can see shifting to the left will cause to produce more precipitate. Therefore, the solubility of calcium fluoride in calcium nitrate is decreased compared to the solubility in pure water. How to get mark for this calculation of solubility? So you are given 1 mark if you write down the dissociation of the salt, 1 mark for writing the expression, 1 mark for the substitution, 1 mark for the approximation, 1 mark for the value solubility of calcium fluoride in the calcium nitrate, 1 mark for the method for finding the calcium solubility, molar solubility calcium fluoride in water, and the value of molar solubility calcium fluoride in water. Next, 1 mark for the comparison, where we mention the solubility calcium fluoride in calcium nitrate is lower than solubility in water. The reason, 1 mark. That's all. Thank you. So wish you all the best for your chapter 7 and your final exam. Okay, bye.